Hi, welcome to our discussion on precipitation measurements. And what we're going to do, we're going to start out by kind of going through the theory behind precipitation measurements, the mathematics behind it. And we'll start out by looking at precipitation rate. We're going to define precipitation rate as the mass flow of liquid or solid precipitation across a horizontal plane over some unit of time, so over some period of time. So that's what we're going to call our mass flow rate. Mass is, of course, measured in kilograms. The area they talk about here would be in meters squared, and then the time, of course, is in seconds. So there's a mass of water flowing across a plane over some period of time. Of course, mass depends upon the density of water and the amount of water that's flowing across that area. So that would be the drop size and the concentration or number of droplets in a given volume of air. Area, of course, we can come up with some imaginary area, divide the mass of water divided by that. And then time is, of course, measured by a watch or a cell phone or other things. We have a timer. So we're going to come up with an equation that takes these variables and puts them together to give you the mass flow rate. And that would be this equation that you see. It's the mass flow rate is, of course, the mass divided by the area divided by the time. So that is your mass flow rate. Now this is a little bit different than a rainfall rate. We're going to define rainfall rate as a measure of the intensity of rainfall by calculating the amount of rain that would fall over a given interval of time if the rainfall intensity were constant over that period of time. That's straight from the glossary of meteorology. The rainfall rate R, of course, depends upon the density of water. So we will take the density of water and take the mass flow rate and divide it by the density of water to give us the rainfall rate. That is not necessarily intuitive, but I'll show you how this works out if you bear with me. So our new equation now is the mass flow rate, which is m divided by a divided by t, and then that m divided by the density of water, rho w. And our equations, if we take the equation for the mass of water, which is the density of water, which is mass divided by volume, and the rainfall rate, which is the mass divided by the density of water divided by the area divided by time. When we combine those two and put m over v in for density in the rainfall rate equation, you can see that the masses cancel out. You've got a volume that comes up top and you got area on the bottom. So volume divided by area divided by time. And you know that volume divided by area, well, volume is the area times the height. So the areas cancel out and you're left with height over time. The height of what? This would be the height of water in a container. In other words, how fast is that water accumulating in the rain gauge over some period of time? That would be your rainfall rate. So there's the water falling in and the height going up. Rainfall rates are typically measured in MKS units, which would be meters per second, which looks like a speed actually, or velocity. But more commonly here in the United States, we typically measure rainfall rates in inches per hour. And in most other countries, they use millimeters per hour. So that's a little bit about the rainfall rate mathematically. And we'll talk a little about the history of rain gauges in our next video.